We're going to be looking at the substitution of a carbon with another carbon. When adding heteroatoms like oxygen, nitrogen, or any halogen, these are also considered substituted groups, but we're going to talk about heteroatoms at a different time. We are solely going to be focusing on moving around carbons and hydrogens only. If we look at N-butane, N is the designation of the parent chain for the molecular formula C4H10. You do not need to know what N represents, but just in case you see it again. When looking at carbon number 2 on our N-butane, when we go to the isobutane, also known as 2-methylpropane, we can see that on carbon 2, another alkyl group or substituent has been added. The iso means that the substituted group moved onto carbon 2. What has happened is we still have C4H10, but a hydrogen from that carbon 2 moved over to replace that carbon alkyl group that moved on to carbon number 2. Right? So we still have that same molecular formula, but we changed the number of substituents or groups on carbon number 2. So when we're looking at how many substituents a particular carbon has, we'll call that carbon classification. That makes it easier and quicker to reference the properties for that particular carbon. A primary carbon is a carbon that is bonded to one other carbon atom. So we're only looking at one carbon at a time, and then how many other groups it is attached to. Therefore, a primary carbon is what we call mono-substituted, or has one other group on it. A secondary carbon is going to have two other alkyl groups on it, and it is di-substituted. Moving forward with this trend, a tertiary carbon is going to have 3 alkyl groups and is tri-substituted. And a quaternary carbon is going to have 4 substituted positions. Knowing the substitution of a carbon helps us predict physical and chemical properties. Looking at physical properties first. As you increase the substitution around a carbon, we're going to increase the potential solubility. So even though hydrocarbons are not readily soluble in water, the more substituted a hydrocarbon becomes, the more spherical in shape it is. The spherical shape is easier to surround with our solvent to allow for a potential increase in solubility. So as you can see in this imagery, that in our first parent chain hydrocarbon, versus once we started one substituted spot versus multiple substituted spots, it becomes more spherical, easier to surround. Then looking at phase change. Remember, phase change is the transition between a solid and a liquid, so melting point, or liquid and a gas, the boiling point. As we increase substitution, we're going to decrease the phase change, or melting boiling point temperatures. The reason being is when you do not have any, or the minimal amount of substituted carbons, you have the largest amount of surface area or contact area that allows the dispersion forces to be maximized, which means if they have a higher attraction with their electron clouds, it's going to take more energy to separate them. But as you start to increase this substitution around a carbon in that compound, you are decreasing the potential interaction between two of those molecules. And then again, further decreasing as it becomes more spherical or more substituted. Therefore, the dispersion forces become weaker as our carbons become more substituted. Chemical properties of hydrocarbons is the ability for a carbon to undergo a chemical reaction. One chemical reaction we know of is combustion, and we learned that back in our general chemistry curriculum. How successful a chemical reaction is determined by the accessibility and stability of the carbons that are going to be attacked or reacted with by another group. So if we are going to burn our hydrocarbons, the process of combustion, the carbons are going to become oxidized, which means we're going to be adding oxygen onto each carbon. That's where the term oxidation actually had stemmed from, is increasing the amount of oxygen. It is more efficient and easier for primary carbons to be reacted with because they're already exposed and have the ability to break and form bonds more readily. They're less protected. Whereas a secondary carbon, it becomes a little bit more crowded, and then a tertiary, this carbon is protected by these three groups. And a quaternary carbon is just very stable. It is well protected by the four groups that are around it. Therefore, the general rule of thumb for reactivity of carbons is that primary carbons are more accessible or reactive than secondary, than tertiary, than quaternary.